Thank you, Paul. Good afternoon, everybody. Old German bon mot is saying the last one is bitten by the dogs. I hope you will not take me so hard. And it is my pleasure to introduce you recent results in the modeling, not of a material or of an electrophysical or optical property, but of a process chain, and a quite complex process chain that is related to the processing of ceramics and cermet powders by the application of advanced thermal spray technologies. Sometimes we call them thermokinetic deposition techniques. And this was a main part, not only in this common project, IP NanoCare, but until now is an important approach in our institute. For those of you who may not be so familiar with the thermal spray technologies, I shall try to give you some principal information and background to these technologies. We'll then explain what we understand about coatings in the sense of composite materials, and then I shall come to the core to this various methods we apply for modeling and simulation of these supersonic fast processes in ceramic technologies, and hopefully the last view in the future is the optimized robot-assisted manufacturing technique. Before I go in detail, I would like to thank my co-workers who have substantially contributed to this work over many years. First of all, Martil Wenzelberger, now an assistant professor at our graduate school in Stuttgart, and Andreas Killinger, and last not least, Esther Dongmo, who is present, and Antonio Candel Ruiz, who is our specialist in robot-assisted manufacturing engineering. So, a few words to the thermal spraying. What does it mean? We have a high energetic process where, with a variety of torch equipments, in any case, we have a high-speed expanding flame or plasma jet, and then we try to load up this expanding jet stream with powders, with solutions, with suspensions, with emulsions, whatever may be useful to produce performing coatings on a substrate. And you see, we like the Swiss, so this yellow guy is not from China, he is made in central Switzerland, and this is a new generation of robots with a very high stiffness and precision in their movement, so that they can handle a torch that has the same power as a jet engine of a military aircraft, but reduced to a tenth or to a thousandth of its volume. What is really occurring in this process is that we have a very fast melting of these original particles by the intensive heat transfer coming from an electric arc, from a plasma discharge, or from an intensive autogenous flame. It can also be a laser employed or a detonation of a gas mixture. The most important feature is how to manage the acceleration, and I am talking about processes that mostly will work in a range of the speed of sound and even superior. I will show you some details in a minute. And now for sure it is interesting what happens on the surface of our substrate that may be a complex machine element. How is this consolidation process going on? And we have learned so much today about complex ceramic systems, but mainly under the conditions of thermodynamic equilibrium. With these very fast processes, it is not so probable that we always achieve the real equilibrium. That means we have to think quite distinctly about the kinetics. The kinetics may be in some cases more important than the thermodynamics, but nevertheless, this basis remains important. An extreme example is shown here. You see, we have a material as a coating with a melting point far beyond 2000 degrees C. And we coat the material, a fruit, an apple, that hardly can stand 60, 70 degrees C without being converted to a nice dessert, as some cuisine chefs like to do it. And the reason is it is never standing, neither the torch nor the apple itself. That means the kinematic arrangement between this high energetic source and our component, our substrate, is a completely new and additional challenge. That means we have to manage this hot gas or plasma plume. We have to manage the mass flow and the mass transition from the source to the substrate. We have to manage the radiation. We have to manage the impact, and so that our substrate can stand these rough conditions, we need a sophisticated type of simultaneous cooling, and we need even sophisticated robot kinematics so that we can combine these extremes to an industrially successful process. And in the next few minutes, I shall try to show you what is the content if we really go in more detail to these techniques. So mainly we can separate between the processes that are driven by the use of a high chemical potential, that means intensive combustion processes, and the second family is the group where we have electric discharge processes. So here we have all the variety of the plasma processes, and here in the turquoise we have these techniques we are a little bit in love with. That is the high velocity oxygen fuel spraying with all its variants, and this leads us to these supersonic fast deposition technologies. What is the main difference? What are the main characteristics between the plasma spraying on one side and the flame spraying, the modern flame spraying techniques on the other side? For sure it is the physical principle, but I have not the time to go in too much detail to that. The main feature is with our plasma sources we can achieve temperatures so high that we can melt every type of material, and we can melt it very, very quickly. But we are limited to a certain extent, referring to the efficiency rate, and this means the deposition rate, and we are limited to the kinetic impact, that means the particle velocity, and if we go in more detail, we have to talk about the velocity distribution, the distribution in space, and this means a multi-dimensional approach. The nice thing is that these processes are operated under atmospheric conditions. So with a background in physical chemistry, this is not like a PVD or a CVD process, a closed system. This is at least a partially open system, and this makes it so much attractive for an industrial application. But some of you may remember that a plasma torch can also be used to cut a huge piece of superalloy. It can also be a cutting device. The same is true for a powerful laser too. Therefore, the question is how to find the most appropriate relative kinematic move between the substrate and the torch. In any case, we have this transition of a solid powder to a temporarily liquid droplet, fine droplet, and the consolidation of many, many droplets to the layer, to our coating. And in the case of a plasma torch, the typical feature is this multilamellar structure, and so you clearly can smell this is a non-isotropic, this is a distinctly anisotropic material in its electrophysical, in its thermophysical properties mainly. And that's the look on top, so we can see the splats at the upper surface layer. So this is more or less the conventional modern plasma coating deposition of ceramics. In contrast to that, the supersonic flame spray. And you can see with a higher resolution, this material looks much more than a hot isostatically pressed or a sintered ceramic. There are no more lamellas. And one of the reasons is that we have a much higher kinetic impact, much denser and better adhering coatings, but the drawback is, to a certain extent, the limited process temperature. So we cannot process any type of ceramic, so there are some limitations, an example with zirconia and its blends. But the nice advantage, and you can see it here in this picture, there are 1, 2, 4, up to 6, 7 nodes. That is the Mach nodes, and you see the gas, the velocity of the gas jet can exceed 5 or even 6 times the speed of sound. And that makes it so challenging to inject now our ceramic powder in this high-pressured combustion chamber, use and employ the strong acceleration, and use the impact to make the product, to make the final coating. But we have this intensive heat and mass transfer and also momentum transfer. And today I will not go in any detail to the experimental results so far, but will show you what is the outcome from the viewpoint of building up a model and use simulation techniques to predict, and not only to predict, but also to optimize the processes. Last but not least, in the introduction, a few words to this brand new technology we developed in the last 3 years, where we employ directly the suspensions. That means direct processing of nano-powders in a workplace safe environment. That means in a suspension, in a closed system, in a closed loop, a high pressure pump, and the direct introduction of these suspension to our torch. This means a completely new design in the combustion chamber, and also an adaptation of the nozzle geometry for the free jet, as I will show you in a minute. So the traditional way is the introduction of gas-fed micron powders. The new technology is the introduction of liquid-fed nanopowder suspensions. The application of these type of coatings covers a broad variety, not only in the machine industry. Professor Manteley knows very well that the paper and pulp industry needs these protective coatings. We have it in the biotechnologies, and the special feature of our Stuttgart development, for sure, in the center of the automotive industries, is ultra lightweight engineering, using lightweight alloy basic components, and just giving them functional surfaces consisting of micro and nano ceramics. But the same is true for a new generation of fuel cells, where we come much closer to complex electrophysical properties. And with the approach of modeling and simulation, this may describe you the challenge, the general challenge in this field of process simulation. This is not a one-step process. It is a process chain. And just in case of the lightweight engines, one example is shown at a poster in front of the audience here. The first step is what we call the substrate, the substrate pre-processing. That means how to prepare the surface, not only to have the best adherence of the coatings, but also to have the best fit of stress distributions. Then we have as an option the selective masking, because in many cases we don't want to coat the complete component, just a part of the functional surface where the value adding makes sense. And then the core business, the coating technology itself. This is a rotating device, but the coating is not enough. True to type, high precision coating is one thing, and the post-processing, that means the precision machining with all its technical and economic challenges, is a further important step. And here you can see the cut through such a 4-cylinder engine where we have just a 80 to 100 micron functional coating instead of the original cylinder liner. So in any case, I try to educate our engineers to understand the complete full process chain to find the most appropriate solution also for the individual steps. So far my introduction. Coatings understood as layer composites. What does it mean? It first means a completely different theoretical approach. Just to combine one material with the other, that is the traditional way, but this cannot be the standards we follow in these years. That means the creation of protective and functional coatings and to combine them with the properties of the structural material as a carrier, this is well known and well understood. But we finally need a reliable structure, and we also need a reliable manufacturing process. And this gives you the first smell that just to combine the two materials by far is not enough. By far is not enough. And one basic reason is that there is a distinct interaction between the two materials, between the coating and the substrate. And not only under operational conditions, not only under testing conditions at room temperature in a lab, no. Also in the conditions of manufacturing, that means in the processing conditions. So therefore we need a deep understanding of adhesion, of chemical compatibility, and the complete set of physical compatibilities. And if you see that people combine lightweight alloys with ceramics, and you see this large difference in thermophysical properties, for sure we have to handle with a problem of high thermal stresses and residual stresses as they result from the process and its histories. So some people see this as a problem or even as a disaster, and they never come to an end. We take it the Japanese way. We say this is the challenge, and if we can manage it, this is the way to create a new set of composite, layer composite products, and therefore we need the full understanding in the theory of residual stress involvement, the analytical tools. We need the experimental setups, and last not least, the numerical stress analysis to understand what is going on in the product. And you have seen and listened to my four speakers that the finite element method is an important approach, but it is by far not enough. The mismatch in the thermophysical properties is well known, but we have again to face that it is also a lot of process-induced influences. By example, the well-established grid blasting or laser structuring and machining or water jet machining in the pre-processing. And this mainly causes compressive stresses. The thermal spray process itself, it will influence, again, a variety of stresses. There are tensile ones, there are compressive ones with respect to time. I will not go to too much details, but we should not forget that any type of post-processing, especially mechanical post-processing, as we need it for precision grinding, polishing, machining, will also be distinctly affected by the contributions of the earlier process steps to the total stress situation in our layer composites. And I will show you that with a simple example. It is the same geometry of a material that is coated, and it is the same type of coating. We will just vary the substrate. Magnesium, aluminum, titanium, and steel. You can read the types in detail, and you can see that there is a distinct influence in the compressive stresses. 0 is the outer geometric surface, and we have developed a method to determine the stress distribution not laterally, but in the depth profile, And what we can learn in a second is that the elastic modulus, that the Young modulus of the substrate material has an important influence to this type of stresses as they occur near the surface or in the interface between the substrate and the coating. Another example, we have the constant type of substrate, we have the constant type of coating, but now we vary the heat transfer. The heat transfer influenced by the type of energy carrier, propane, always plus oxygen as the combustion mixture, here a liquid energy carrier, kerosene with oxygen, and for comparison, 2 types of plasma coatings, one of them with additional simultaneous cooling. And wow, what we can see here, there is even such a strong variation that we shift from compressive to tensile stresses. And in an amount that is not so much for a modern bulk ceramic, for a solid structural material, but it is sometimes critical for the tensile strength of such a coating material. And latest, if you have learned this lesson, you may guess that it is indispensable to manage, to understand, to control the occurrence of these thermally and process-induced stresses. The last example to show the importance is the variation, is the variation of the cooling. 3 times the same material, the same substrate, the same geometry, the same design, just varying without any cooling, the red line, with a traditional compressed air cooling and quite intensive cooling with liquid carbon dioxide plus compressed air cooling. And you see again, we can vary the stress distribution by more than an order of magnitude. So, we can summarize. The substrate plays an important role, the heat transfer plays an important role, the mismatch in thermophysical properties plays an important role, and there will be further important factors that will influence these stress distributions, and they are essential for the reliability and for the functionality of our final product. An extreme example is shown here. This is a so-called ozonizer tube. That was a precision glass tube with a metal electrode and a ceramic dielectric on top. And this is the same product, a little bit different magnification. That's how it looks. A boron silicate glass as a carrier, and this double layer in a situation with well-balanced residual stress distributions. And this can happen if you leave for lunch in the morning, your piece looks beautiful, and you come back and you think, oh, there was any foe who has destructed my sample. It was just the critical amount of residual stresses that bring the piece to something like an explosion. Not so harsh, but the same effect will occur if we have a non-desired deformation of the sample. That means every detail related to dimensional tolerances is also connected with this subject residual stress distributions. Okay, as I mentioned before, we have to overcome this problem, and therefore it is essential that we do not understand the final result, but we have also to measure the temporarily occurring stresses during the various manufacturing steps and the residual stresses. Both groups have to be investigated. And therefore, we need the theoretical background, and again, we need the experimental setup, and we have to match it with the calculations by numerical stress analysis. Which can be the tools? Principally, we have the mechanically destructive methods. They have sometimes been adapted from critical components in the nuclear plants. We have the mechanically partially or only locally destructive methods, and there are the well-known non-destructive, we call them the pure physical methods. They have all their advantages and disadvantages, but it is important to know what is their lateral and depth resolution ability. And so we can see that in the case of this type of coatings, varying from 10 micron to maybe 500 micron, this quasi-non-destructive technique, what we call the micro-hole milling and drilling method, is a quite appropriate one, and we try to combine it with X-ray analysis and also with magnetoacoustic analytic tools. So, an intermediate summary let us show that the understanding of the material properties is an essential, for sure. And it is also for sure that we have to manage all the parameters related to the thermal spray process. We have forgotten one field, and this is what happens with our component under operational conditions. Thermal stresses, residual stresses was one thing. But imagine what happens in a Formula One racing car's engine. It will start at the beginning at room temperature, not as cold as we have it in Northern Europe just now, but then it will run up to a temperature close to the turbocharger, 600, 700 degrees C, surface temperatures. That means we have also to think about the operational load stresses, the mechanical ones, and the thermal stresses that occur in the final mechanical system. And last not least, the modeling and simulation is now the essential tool to understand, to calculate, to estimate the interaction between the stresses that are occurring from our process and the interaction with the operational load stresses. So the analytical tool is shown here. That is the so-called microturbine. We measure the surface stresses, and these surface stresses are transferred to the strains in the depths at the bottom of the hole we create by this micro machining operation, and we calculate the stress depth profile by the stepwise drilling and milling operation. So typically 5 micron stepwise from the surface to the bottom, and this allows us, depending a little bit on the material, to analyze the stress distributions up to a depth of 1 millimeter. So this shows such a typical hole, and you see this is also a mobile equipment that is used not only for the measuring of stresses in passenger car engines and sports cars, but also for jet engine components. So the calibration curves, that was a lot of hard work for Martin Wenzelberger and his team to calibrate the various sensors employed in this technique, so that step by step, by a more and more finer calibration, the more reliable are the results. So here we have the first time the finite element technique employed, where we take the quarter plate, where we bring down the bore, and now we can decide what is the resolution we prefer to understand it, and it is not just the meter scale or the centimeter scale. It is no problem to go down also to the micrometer scale. Finite element method, an essential for mechanical engineers, and quite interesting to understand these layer composite, that is our product, the layer composite properties. And again, the most exciting example for our young engineers are these high-end engines. And if you look to such a 12-cylinder engine of the present technology, the total weight is not superior to a 4-cylinder engine with 10% of the performance of 30 years ago. And the reason is, it is no more heavy gray cast iron with centimeters of wall thickness. It is an ultra lightweight special aluminum alloy, and just on top, we have a ceramic coating, in some cases with an additional bond coat, and this is the core of the process assembly, where we have again these high stiffness, high precision robots, and you see the torch with this jet, and now we have to think about the best fit of the kinematic arrangement of this supersonic flame spray jet versus our substrate. So I will not talk about the nice material properties. This is published in quite more than a dozen of papers. Today our focus is the challenge to optimize the microstructure of this material and to optimize the stresses and the stress distributions. If these two challenges can be overcome, we can really exploit the beneficial material properties. Okay, so the first step we have to perform is to understand the behavior, the compatibility between our ceramic coating and the light metal substrate in this case. And you see the big difference in the thermal expansion of the two components, and it is not so easy in this case to use a plate. At least we start with a cylinder. I will show you more complex geometries in a minute. And what we have to do first now is to simulate the heat transfer, the heat input into the coating, into the substrate material, and to understand the various phenomena of heat conductivity. So this is the typical setup of the finite element model, and we started to use it with pure elastic properties as a most simple approximation, and there are further approaches to go in more detail with elastic plastic behavior and some further variations. What we have to see is that it is a system of solid brick elements, and we have sequentially coupled the temperature stress fields. And therefore the method is also called coupled temperature stress field analysis. And to limit the computational effort, there is a linear interpolation for small strains due to the limited capacities. So some of this work can really be done with a modern personal computer. You have not the need in this case. In other cases, we have it to get access to a high-performance computer center. Simultaneous cooling is an important process component we must understand, so that we can really find a good fit for the total heat transfer. And just to show you the three main systems, here we have two injectors, rectangular to the plasma torch, The tube itself, the cylinder of this engine, is in rotation. Here a different arrangement with a fan, with an additional fan with about 1 dozen of nozzles. So we have the compressed air plus the liquid carbon dioxide cooling. And here one of the most sophisticated simultaneous cooling systems with two cold spots, not only the hot spot, two cold spots. And just to give the beginners an idea, with a plasma jet with more than 3,000–4,000 K on the surface, we can handle it so that the substrate will not exceed a total temperature of 60 or 70 degrees C. That means the effects of this simultaneous cooling are crucial and are one of the most important tools in our hand to overcome the misfit in the original material's properties. So, now the results of this finite element analysis and simulation for the thermal spray process of ceramics on light metals. And we may start left-hand side in the case of just the coating deposition. That means here we show the mass transfer. So let me see if the mouse works. Oh, great. Piece is under rotation. Here it is shown with a fixed piece, but you may easily imagine, and step by step we change in the finite element mesh, we change the first set of meshes on the surface to the material properties, no more of the substrate, but to that of the coating. So now it is finished. And in the second, we show the temperature distribution. You see the hot spot, which is just occurring on the surface, a spiralic geometry, but the material itself is not overheated. And on the right-hand side, we had the mass transfer, the temperature evolution, and now we have the stress evolution. And you see there is a quick relaxation when the hot spot is traveling over the internal surface of the cylinder. So these were the first steps in understanding this process. Another important factor is to understand what is the deformation. Is there really only a pure elastic deformation, or is there a small amount of plastic deformation, which will mean we cannot obtain the original dimensional tolerances? And this is really crucial, especially in the example when BMW brought up a new engine